Good afternoon. In this video, we're going to be going over series, parallel, and combination circuits and how to deal with these circuits mathematically. This is a required video for the PhysEng course. Make sure you are watching this video so that you're going to be able to do these practice problems when we're working on them in class or on a free response test. We're probably not going to be going over this method in class. This video is going to be one of the only ways you're going to get this instruction. So, starting off first with a simple series circuit, we got a 1 battery, 3 resistor circuit right here. You can see we know a voltage and we know 3 of these resistances. What I want you to do is sketch this circuit. Go ahead and sketch it down on your sheet of paper and fill in as much of this table down here that you can. V total, I total, and R total refers to the total quantities, whereas V1, V2, V3, I1, 2, and 3, and R1, 2, and 3 refers to the resistance at resistor 1, 2, and 3. Okay, I've filled in our simple knowns. This is just exactly what the diagram gives us. It tells, hey, the total voltage is 60 volts, and each of the resistances on each resistor. But we don't know any of the current, we don't know any of the voltages individually across each of these resistors, and we don't know the total resistance. To move on, we need to go over some simple rules about series circuits that we discovered when you guys were doing the circuit lab. First off is the total voltage in a series circuit is equal to the sum of all of the individual voltage drops across each resistor. In this case, that's going to be V1 plus V2 plus V3, and so on for however many resistors we have. Current in a series circuit, that's the easy one. Current in a series circuit is equal everywhere. So the total current is equal to current 1, equal to current 2, equal to current 3, and so on. So if we're able to find the total current in this column, or any of these currents, we know we've solved this entire column down here. We know the current everywhere if we know it at one point in a series circuit. For resistance in a series circuit, the total resistance, as I add more resistors, I'm adding more resistance. So the total resistance is just the sum of all the resistors, R1 plus R2 plus R3, and so on. Our first step, because we know R1, R2, and R3, is going to be to find the total resistance, which should be pretty quick and easy. To find our total in this case, we want to take our 6 ohms plus 10 ohms plus 14 ohms. Excuse me, that's a 14. Okay. Add these all together. Our total resistance is going to come out to 30 ohms. Now what this means, this RT term, that means if we were to stick all of these resistors together, if we were to zoom out and look at them as one single resistor, that would be equivalent of a single resistor with 30 ohms of resistance. We can now put this aside and let's redraw the circuit. So this circuit right here is equivalent to the same series circuit with a single resistor. And now instead of 3 resistors, we have a single resistor of 30 ohms. That's our total resistance. We still have a 60 volt battery over here. Now, using our very simple V equals I times R, that's our Ohm's law. Using V equals IR, we can find the current, the total current throughout this total thing. Current here is going to be the voltage total divided by the resistance total. Let's go ahead and say that's the total current. So our total current is 60 volts divided by 30 ohms. In this case, 2 amps. All right. 2 amps is our total current. And again, because we know current is the same everywhere in a series circuit, we can say it's 2 amps at all points in this circuit. Using this info now that we know the current at each point in this circuit. Let's put that info aside. And let's look at the individual voltages across each resistor. Let's just look at resistor 1 right here. I just want to look at resistor 1. I want to look at the voltage 1 right here. Well, I know the current here. I know the resistance here. So I want to use V1 equals current 1 times resistance 1. V equals IR. Hey, I know the current is 2 amps. I know the resistance is 6 ohms. Pretty easy. The voltage is going to be 12 volts. Let's look at resistor 2, voltage 2. Remember, this is voltage 1 up here. Voltage 2, same thing, current 2, resistance 2. This time we've got, still have 2 amps for our current, 10 ohms for our resistance, 20 volts for our voltage 2. And for the final voltage 3, we can either do V3 equals I3 times R3 again, or we could just subtract 20 and 12 from 60, giving us a voltage of about 28. We can also double check that. V3 is going to be current 3, that's 2, times resistance 3, that's 14, and that's 28 volts. So there we go. We've now solved all unknowns in this series circuit. Let's move on to parallel circuits next. Before I can really talk about parallel circuits in detail, we need to go over how to find the total resistance of a parallel circuit. So we're not going to solve the whole thing right now. We'll do that in a second. Let's just look at the total resistance. We know R1, R2, and R3. Well, in a parallel circuit, we can't just add up all the resistors to get the total resistance. Remember, parallel circuit is a little counterintuitive in that as we add more resistors, if I were to add more resistors over here, it actually decreases the overall resistance because it's like adding more lanes onto a highway. More paths for the current to travel means it lowers the overall resistance of the device. The rule for resistance in a parallel circuit is the inverse 1 over the total resistance, 1 over RT, equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, and so on. Okay, we've got our 3 resistors right here. We don't know our total yet. We've got 1/5 plus 1/20 plus 1/4. Remember, 5 ohms goes down here, 20 ohms goes down here, 4 ohms goes down here. You can either plug this into your calculator or try some mental math. I'm going to go ahead and leave the math up to you guys and just present the final answer up here. All right, for my final result, we've got 1 divided by RT equals about 1/2, or total resistance equals 2, oops, not current, this should be 2 ohms. So, again, this circuit, this parallel circuit, is equivalent to a circuit that has a single resistor in series, and that's going to be a 2 ohm resistor. Sometimes you'll also see R total called R equivalent. That's because these 3 circuits in parallel is equivalent to a single 2 ohm resistor that we just calculated right here. Okay, here's a simple 2 resistor parallel circuit. You'll notice we've got the full table down here. Already we know that 24 volts, that's our total voltage up here, or our external voltage out here. Our total, we don't know yet, but we do know that R1 is 12 ohms, R2 is 24 ohms, and we've got no current meter hooked up to this, so we don't know any currents in here. First step is going to be to find our total resistance. Looking for that first. But before we do, I need to back up, and let's talk about some simple rules for parallel circuits. And this is a little bit opposite to what we've got from series circuits. Remember, in a parallel circuit, the total voltage is equal to the individual voltages across each resistor. That means V total equals V1 equals V2. If we had a V3, it would be there, and so on. The current in a parallel circuit gets split up. So if I've got current total coming in right here, it has to split up into current 1 and current 2. This means that the total current is equal to the sum of the individual currents. You can kind of see how this is the flip-flop of series circuit. In a parallel circuit, we add up I1 plus I2 plus I3, and so on if we've got any more. And as we went over in the last slide, the total resistance is, the inverse of the total resistance is 1 divided by R1 plus 1 divided by R2, and so on in this case. So usually our first step is going to be to find the total resistance. Now it might not be the first step in every case, but in this problem, that's what we're going to do first. We've got 1/12 and 1/24. Now instead of plugging this into my calculator, I'm going to do a little mental math here. We know that 1/12 is the same as 2/24. Total down here is going to be 3/24. That again is equal to 1 over total resistance. Let's take the inverse of that. I've been lazy with my units here. I've been lazy with my units. Don't get lazy with yours. Our total resistance here is 8 ohms. So we know that this circuit is equivalent to a single series circuit with a single resistor of 8 ohms. This means we can find total current using just good old V equals IR. Let's get this small over here. We're going to start off with V total equals current total times resistance total. V total is our 24 volts. Current total is our unknown. Resistance total was our 8 ohms. So hey, in this case, current total is another 24 divided by 8, and that's 3 amps. Now I can't say that current 1 is 3 amps. I can't say that current 2 is 3 amps because it's getting split up here. What I can do though, hey, I do know that the voltage from this point to this point is 24 volts. I know the voltage from this point to this point is 24 volts. Again, I know this from our simple rules for a parallel circuit. So what I can do, using this information, I can solve for I1 and I2. I don't even need to know the total current, but it might come in handy just to check that my I1 plus I2 sums up to my I total. All right, let's look at R1 first. V1 equals current 1 times R1. Current 1 is going to be V1 over R1. That works out to be 24 volts over 12 ohms, or about 2 amps in this case. So, all right, we should be expecting 1 amp for our current 2, because 2 plus 1 is going to give us our 3. I think you guys can see that we're not going to have a problem with that. Current 2 is 24 volts divided by 24 volts, 24 ohms. No problem getting 1 amp down here for current 2, and you guys can see that current 2 plus current 1 is adding up to current total. So this is how to deal with a parallel circuit. Maybe the hardest part of this might be doing the equivalent resistance calculation over here. As long as you're keeping good track of that, it's very similar to series circuit. It's just you flip the rules, you sum the currents, and you have a single equivalent voltage. We're going to move on to a combination circuit next. All right, we've got a combination circuit, and as the name implies, it is a combo of a series circuit and a parallel circuit. We've got this R1 out here, which is not in parallel with R2 and R3. What I want you to do first, and note the current, we've got some current information down here. See if you can pause the video right now, sketch out this circuit, and see if you can fill in as much of this table as possible. Go ahead and pause this video and do that right now on your own. Fill out as much of this table as possible. Okay, it seems kind of tough because if you'll notice, you probably started looking for VT over here on the left, and you notice it's not there. We don't know what the total voltage is, but we do know what the current is, but we only know the current in this exterior part of the circuit. This is where our I1 and our I total is going to be. Essentially, this part out here is equivalent to a series circuit, and so for that part, we can say current total and current 1 are the same thing. So we could probably find voltage 1 just using this information, but I'm going to hold off on that for now. I want to look at the total resistance first. Now you might be thinking, well, okay, I can't just use the rules for series. I can't just use the rules for parallel. I've got a combination of the two. What we want to do is let's zoom in on this part of the circuit right here. I'm going to call the total resistance of just these two resistors, I'm going to call this R equivalent. That's R EQ. So that's the equivalent resistance of these two resistors right here. Now let's use our rule for parallel circuit. So 1 divided by R EQ equals 1 divided by 5 plus 1 divided by 20 in this case. 1/5, that's the same thing as 4/20. So our 1 over R EQ is going to be 5/20, or our R EQ 20 divided by 5 ohms, that's 4 ohms right there. So now we know we've got a 4 ohm resistor for this equivalent resistance right here. Let's put this info to the side. And let's redraw this combination circuit. We don't know the voltage yet. I'm going to say this resistor right here, that's the same thing, REQ, as having a single REQ in series with the rest of this circuit. We've got R1 over here, that's our 5 ohms. So now we have simplified this combination circuit into a series circuit. Our total resistance then, we can use the rules for series resistance addition. Our total resistance is going to be our 4 ohms from our equivalent resistance plus the 5 ohms of resistor 1. Total resistance here will be 9 ohms. So at this point, excuse me. At this point, we can treat either one of these drawings as equivalent. I'm going to look at the drawing of the series circuit for a second. Now again, I didn't somehow replace these two. These two drawings are equivalent to each other. That's why we're using the terms are equivalent. Let's say now I want to deal with this single circuit right over here. I want to deal with this series circuit. My voltage is unknown, but I do know the current, and that's our current total. I know the current up here is our 4 amps. I know my resistance total is, that was our 9 ohms. we want to find the voltage of our battery over here. Well, that's pretty easy. Voltage is current times total resistance. In this case, total current times total resistance, because I'm looking at this single series circuit right here. Our total voltage is going to be 4 times 9, which is 36 volts. That's a weird looking battery. I've never seen a 36 volt battery over here. But that's the info we have for our total voltage, 36 volts. Okay, getting closer, getting closer. Now we have enough info to look at individual parts of this as they come along. Let's figure out the voltage for R1, our voltage number 1. Voltage 1 is going to be current through 1 times the resistance of number 1. Okay, we know both of those. Current 1 is 4 amps. Resistance 1 is 5 ohms. Oops. Yes, it's 5 ohms. So, voltage across number 1 is going to be 20 volts. V1 is our 20 volts. Let's put this away. Now this was where it might get a little complex. Let's bring back our drawing of our series circuit over here. Remember our rules for voltage in a series circuit. They all add up. So I know if I lose 20 volts across here, across resistor 1, how many volts do I have across the equivalent resistor? Well, if I lose 20 volts here, I've got 16 volts across here. This means, let me draw this for you. This means that from point A to point B, I've got 16 volts. From point C to point D, I've also got 16 volts. Let me write that down. Our total voltage, let's call that voltage 1 plus voltage equivalent. Now that's only going to be true for this specific configuration. If I've got a different configuration of a combination circuit, I might be writing down a different total voltage equation. You got to just look at the problem and write it down for yourself. This is not going to be the same for every single circuit. This is just true for this circuit. Our total voltage was, now this is what I just did, our total voltage was 36 volts. Voltage 1 was 20 volts. So our voltage equivalent is going to be 16 volts. Let's walk over here. Now, voltage equivalent is the same thing as the voltage in a parallel circuit, because now we're looking at the parallel section of this circuit. So VEQ is going to be the same for V2 and V1. We could also write that as VEQ equals V2 and V3. Voltage equivalent equals V2 and V3. All right, we are closing in on the home stretch. Now we know V2, we know R2. We're going to, again, use V equals IR to find some current. V2 equals I2 times resistance 2. In this case, V2 is 16 volts, R2 is 5 ohms. I'm not going to plug that into my calculator. I'll let you guys handle that on your own. And current 3 is going to be 16 volts divided by 20 ohms, or about 0.8 amps. let's go back and let's do 16 divided by 5. Gives us our 0.2 amps over here.